cruise ships don't generate power the way you think, hiding something so powerful beneath the water that it can run a city without ever plugging into the shore. Deep inside the ship's hull sits an actual industrial power plant. A large cruise ship holds 4 to 6 heavy-duty diesel generator sets running on heavy fuel oil. Instead of connecting directly to the propellers to push the vessel, these massive engines power large alternators. The alternators convert raw mechanical energy into electrical current, sending power straight to a central switchboard. From here, the system distributes high voltage power to the propulsion motors and the rest of the vessel's systems. The amount of electrical current flowing through the switchboard down below is enough to power a small town without a single blackout. Engineers use this diesel-electric setup because it gives the ship precise control. Rather than forcing the propeller shaft to spin at the same speed as the engine, the electricity allows the engines to run at one efficient speed while the electric propulsion motors adjust independently. This design cuts down on heavy vibrations and saves fuel when moving at low speeds. Traditional diesel engines mean burning through thousands of gallons of fuel daily. To cut down on emissions, engineers started looking at cleaner alternatives like marine gas turbines. These jet-style engines work by pulling in outside air, compressing it, mixing it with fuel, and continuously burning it to spin a high-speed turbine. While they burn much cleaner than heavy marine diesel and keep sulfur emissions way down, running them over long distances costs an absolute fortune in fuel. To offset this financial hurdle without losing speed, vessels like the Queen Mary II uses a smart hybrid setup. Traditional diesel-electric engines for the baseline hotel loads and slow cruising. Gas turbines are for extra power to maintain its transatlantic schedule. This hybrid combination allows operators to balance strict environmental regulations with the sheer mechanical output required to move the heavy hull. Integrating these distinct power sources requires complex switchboards that can handle massive sudden shifts in electrical load without cutting power to the kitchen units or the staterooms. The engineers have to keep a super close eye on how much fuel feeds into these turbines, making sure the ship has enough power for tricky maneuvers or rough seas without the fuel bill absolutely exploding. But running a vessel on a completely carbon-neutral power plant is another challenge altogether. Leaving behind the nuclear debate opened the door for new green solutions, including the return of technology used hundreds of years ago. Modern naval architects are rethinking fuel usage by looking at the oldest propulsion method in history: wind. Companies such as Hurtigruten and Ponant are testing sail-assisted ships to help reduce the daily load on the main engines. We aren't talking about the simple, unpredictable canvas sheets of the past. Today's ships use computer-controlled, rigid wing sails that automatically read the breeze and pivot to catch the perfect gust. When the wind fills these structures, they actually push the hull forward, taking a massive amount of strain off the main engines. Using wind assistance lets the ship cruise at a steady pace without working the heavy mechanical components down below to the bone. The system relies on smart sensors that constantly read wind angles and drag. They trim the massive sails on a central pivot by themselves, meaning the crew doesn't have to touch a single rope. It provides a steady stream of clean power that significantly cuts down on how much bunker fuel the ship burns during a long voyage. While the open ocean relies on these fuel-saving methods, the power demands change drastically the moment the ship arrives in port. When a giant cruise liner pulls into a modern terminal, the engineering crew is focused on a completely different task. The massive generators are shut down, yet the ship still needs to run the hotel services, keep the staterooms cool, and supply power to the galleys. Instead of burning diesel and pumping exhaust into the middle of the city, the crew connects the vessel to a shoreside power, a process known as cold ironing. Plugging a ship into the local grid requires high-voltage cables and transformers capable of handling massive amounts of current safely. think of it as plugging a massive floating resort into a giant wall outlet. The shore power system routes thousands of volts through heavy-duty cables directly into the ship's main switchboard, allowing the crew to turn off the onboard engines completely. This cuts down on noise and completely removes localized emissions while the ship is docked. Understanding how this energy works on the move is just one part of the puzzle. Inside the hull, the power must be routed through massive electrical conduits. Inside the engineering space lies the main switchboard. When thousands of guests wake up and turn on their stateroom appliances, the system experiences massive fluctuations. If the power supply isn't regulated perfectly, the entire grid could trip, leaving elevators, light, and kitchens in the dark. The main switchboard acts as the absolute brain of the ship's electrical grid, instantly shifting power from the heavy propulsion pods over to the galleys when it's time for the evening dinner rush. To make this happen behind the scenes, smart circuit breakers and load balancers constantly talk with the generator rooms. If the ship is cruising slowly and the electric pods don't need maximum torque, the system automatically siphons that leftover electricity to power heavy hotel loads like the water desalination units and the massive kitchen freezers. Moving all this energy is impossible without the giant cooling system located deep in the hull. Hidden auxiliary systems keep the entire resort functioning. When you drink clean tap water in the middle of the ocean, you rely on giant refrigeration compartments and reverse osmosis units. The electrical grid feeds massive amounts of power directly to these essential components. The reverse osmosis plant takes in seawater and forces it through semi-permeable membranes to filter out sand and impurities. These auxiliary pumps filter thousands of gallons of seawater daily, ensuring the city at sea stays hydrated and fed. To keep food fresh across a multi-week voyage, the auxiliary rooms use dedicated chiller circuits. These systems maintain enormous walk-in freezers, ice makers, and air conditioning compressors for every stateroom on board. The sheer amount of electricity required to run these units day and night places a huge continuous load on the ship's generators. All of this power generation produces extreme heat, requiring a massive heat exchange network to keep the machinery from failing. As the cruise industry modernizes, shipyards are building massive vessels powered by liquefied natural gas. Burning LNG produces far less sulfur and carbon emissions than heavy marine diesel, making it one of the most practical options for large fleets today. However, switching to this fuel source completely changes the engineering dynamics inside the hull. Instead of standard fuel tanks, the ship must be built with thick, insulated cryogenic fuel tanks to keep the gas in a liquid state at extremely low temperatures. The entire fuel infrastructure had to be rebuilt from the ground up to support this clean burning transition. The engines use advanced gas emission systems to carefully mix the fuel before ignition. These systems are highly effective, but they require complex venting and vapor recovery units to ensure safety. This complete redesign of the engine room highlights the heavy engineering commitment needed to reduce the environmental footprint of modern maritime travel. The next time you see a cruise ship lit up in the middle of the ocean, you know exactly what is humming beneath the waterline.